Hello everyone, this is Arshpreet Kaur, roll number 1911-2015. I'm representing a topic on steady and transient heat transfer of heat transfer. Uh, Let us first of all discuss what is heat transfer. Heat transfer is the movement of heat energy from one substance to another. Heat, that is a form of energy, always moves from warmer substance to cooler substance. Like given in the figure, every uh, every hot every hot substance emit energy towards the cold one. Like taking an example of a cup of tea, which is placed at room temperature. The temperature of the cup is more than the room temperature, therefore, it loses its energy and cools itself. Heat will continue to move until both substances are at same temperature. There are three types of heat transfer. First is conduction, next convection, and third one is radiation. Let's discuss about conduction. What is conduction? The transfer of heat between two solid bodies called as conduction. It depends on the difference in temperature of hot and cold body. Here let us take an example. Example of conduction heat transfer is two bodies at different temperature kept in contact with each other, which we are taking example of cup of tea, and let's take an example with a glass having ice. The both are example of conduction. With conducted the cup of tea or the hot body radiates, or the hot body conduct hot waves, and the cooler one radiates cool. Another example is heating one end of the metal like copper. Due to conduction, heat transfer of the other end of the metal is also get heated. The transfer of heat between the solid surface and the liquid is called as convection heat transfer. Let us take an example. Consider a vessel of water being heated. In this case, heating of water due to transfer of heat from the vessel is convection heat transfer. And then radiation. What is radiation? When two bodies are at different temperatures and separated by distance, the hot transfer between them is called radiation heat transfer. In case of conduction and convection, heat transfer, there is a medium to transfer the heat, which may be a solid, which may be a liquid, or which may be a gaseous. But in case of radiation, heat transfer, there is no medium. The radiation heat transfer occurs due to electromagnetic waves exist in the atmosphere. One of the most important example of radiation is the heat of the sun coming on the earth. Then let us see the classifications of conduction heat transfer, which is steady versus transient heat transfer. Next is multidimensional heat transfer, and last is heat generation. Let us see the main topic of ours, that is steady and transient heat transfer. First of all, what is steady state heat transfer is? What is steady state heat transfer is? steady implies no change when time at point within the medium. Like we see in the picture, the first wall having temperature of 15 degree on the one side and 7 degree on the other side. The rate of heat transfer is constant, which is Q1. In the second picture, there is also same temperature of the wall on the both side, that is 15 and 7 degrees Celsius. Therefore, the heat transfer is constant in both the states, that is steady heat transfer means the heat transfer in the both cases are steady, or the temperature is same after some time. Like in time t1 the temperature is q1, therefore then at time t2 the heat transfer is also t1. That is constant heat transfer, which is known as steady heat transfer. Heat transfer through the wall of a house can be modeled as steady and one-dimensional. Steady heat conduction in plane walls. In plane walls, the temperature of the wall in this case depend on the direction. Let's say the direction is x direction and can be expressed at Tx. Let's see this wall. The temperature of all the sides, or we can say parts, is different. The starting part is 20 degrees Celsius and then it reduces its temperature to 11 and then 3 degrees Celsius. The heat transfer is constant, that is Q. The rate of heat conduction is a specified direction is proportional to the temperature gradient, which is the rate of change in temperature with distance in the direction. That direction means the x direction we are considering. One-dimensional steady heat conduction through homogeneous material is given by Fourier law of heat conduction. That is, Q is equals to minus Ka dt by dx, where Q by E is equals to a small q, which is heat flux, is equals to minus Q dt by dq, where small q is heat flux, heat conducted per unit time per unit area, and capital Q is rate of heat flow. Capital A is area perpendicular to the direction of heat flow. dt represents the temperature difference between the two surfaces across which heat is passing, and dx is thickness of material along the path of the heat flow. The ratio dt by dx represents the change in temperature per unit thickness, that is the temperature gradient itself. The negative sign indicates that the heat flow is in the direction of negative temperature gradient. So, heat transfer becomes positive. The negative sign is minus K A dt by dx. That negative signs indicates the heat flow in the direction of negative heat temperature gradient. The proportionality factor K is called the heat conductivity or thermal conductivity of material through which heat is transferred. The Fourier law is essentially based on the following assumptions. First assumption which we take is steady state conduction, that is temperature at fixed point does not change with respect to time. Second, one-dimensional heat flow. Third, material is homogeneous and isotropic, that is, thermal conductivity has a constant value in all directions. Fourth, constant temperature gradient and a linear temperature profile. Fifth, no internal heat generation. These are the assumptions which we take in Fourier law. The Fourier law helps to define thermal conductivity of the material, that is capital Q equals to minus Ka dt by dx, where K is thermal conductivity of the material. If we have to find the value of K, then the formula becomes Q by A dx by dt with negative sign. That is it's K is equals to minus Q by A dx by dt. Let us assume dx is equals to 1 meter and area is equals to 1 meter square and dt equals to 1 degree Celsius. Therefore, we obtained Q equals to K. Here we can't use negative sign as the negative sign indicates with the temperature, that is temperature gradient, that is with dt by dx. Therefore, K is equals to Q. Hence, the thermal conductivity may be defined as the amount of heat conductivity per unit time across unit area and through unit thickness, when a temperature difference of unit degree is maintained across the boundary surface. Unit of the thermal conductivity is given by K is equals to minus Q by A dx by dt. Let's see the heat transfer through the plane wall. Here's the diagram of plane wall. The temperature of the both ends of the wall is T1 and T2 respectively. The thickness of the wall is L and the Q is heat flow. Then we use the Fourier law, that is Q is equals to minus Ka dt by dx. Let's taking a constant C1 and changes the equation in the form of Q is equals to minus Kax C1. Now Q is equals to minus Ka, temperature difference is T1 minus T2 and the thickness of the wall is L. Therefore, we form the formula equals to Q is equals to Ka T2 minus T1 by L. Here by mistake I'll write here T1 minus T2, but here's the answer is T2 minus T1 by L. Thermal resistance concept. Now let's see the thermal resistance concept. Here the thermal resistance concept is thermal conductivity through a wall. Here the diagram represents the zigzag portion, that is, this is the wall which is in the form of we can say resistance. This is representing heat flow, and the picture below this represents the electric current flow, which is actually resistance and all. Let's see. Q conduction wall is equals to that we conclude Ka T2 minus T1 by L. Q conduction wall is T2 minus T1 by K wall, R wall, that is a resistance, or we can say the resistance of the temperature, that is R wall is thermal resistance of the wall against heat, which is equals to L by Ka. Thermal resistance of a medium depends on the geometry and thermal property of the medium. I is equals to V1 minus V2 by Re, that is the current, and Re here represented L by sigma E A. The rate of heat transfer in the electric current, the thermal resistance is electric resistance, and temperature difference is voltage difference. Newton's law of cooling. Now see the Newton's law of cooling. Q convection is equals to HAS Ts minus T infinite, where AS is surface area and Ts is temperature of the surrounding. Convection resistance of the surface. The thermal resistance of surface against heat convection is R wall equals to H1 by HAS, that is surface area. When the convection heat transfer coefficient is very large, then H tends to infinite, the convection resistance becomes 0 and Ts becomes equals to T. When that is, the surface offers no resistance to convection and thus it does not slow down the heat transfer process. In this situation is approach in practice at surfaces where boiling and condensation occur. This is the situation of boiling and condensation. Transient heat transfer. Let us discuss about transient heat transfer. Transient implies variation with time or time dependence. In this picture, we have seen the two times T1 and T2, that is, we have taken 2 p.m. and 5 p.m. In first picture, the temperature of the both end of the walls are 15 centimeter and 7 centimeter. In this case, the rate of flow is, or we can say heat flow is Q1, and in the second picture the time is 5 p.m. The difference, the both end of the wall is changes now its temperature, that is from 15 degree Celsius it changes itself to 12 degrees Celsius, and from 7 degrees Celsius it changes itself to 5 degrees Celsius. Therefore, the heat transfer changes itself as the formula of the heat transfer is equals to minus Ka, temperature difference by length of the thickness of the wall. In transient heat conduction, temperature depends not only on the position in the solid but also on the time. So mathematically, this can be written as T equals to T x, y, z and x, y, z and tau, where tau represents the time coordinates. Typical example of transient heat conduction: heat exchanger, boiler, tubes, cooling of IC engine cylinder head, heat treatment of engineering compounds and quenching of ingots, heating of electric ions, heating and cooling of buildings. Lamp system analysis. Let's see the lamp system analysis, Newtonian heating or cooling. In lamp system analysis, the internal conduction resistance of the body to heat flow, that is L by Ka, is negligible compared to the convection resistance, that is 1 by Ha at the surface. So, the temperature of the body no doubt varies with time, but at any given instant, the temperature within the body is uniform and is independent of position, that is T equals to T tau only. Practical example of such cases are heat treatment of small metal pieces, measurement of temperature with the thermocouple or thermometer, etc., where the internal resistance of the object for heat conduction may be considered as negligible. Consider a solid body of arbitrary shape, volume V, mass m, density rho, surface area capital A, and specific heat, that is Cp. To start with, at that tau is equals to 0, let the temperature throughout the body be uniform at T equals to Ti, that is initial temperature. At instant tau is equals to 0, let the time be suddenly placed in a medium at a temperature with temperature of Ta. Here's the body, that is arbitrary shaped body, where m is the mass, v is the volume, rho is the density, and Ts is the surface temperature. Writing an energy balance for the situation. Amount of heat transferred into the body in the inward interval d tau is equals to increase of the energy of the body in time interval d tau, that is Ha bracket Ta minus T tau d tau equals to mCp dt minus rho Cp v dt. Since m is equals to rho v, therefore d tau minus dA by d tau by minus dA minus Ha by rho Cpv d tau, where dt is equals to d bracket T tau minus Ta. Integrating between d tau is equals to 0, that is T equals to T initial, and tau, that is T equals to T tau, that we obtained log T tau minus Ta by Ti minus Ta equals to minus Ha tau by rho Cp by V, that is T tau minus Ta by Ti minus Ta equals to exponential of minus Ha tau by rho Cpv. Now let rho Cpv by Ha is equals to T, where T is known as thermal time constant and has no unit of time. Therefore, equation 3 is written as T tau minus Ta by Ti minus Ta is equals to exponential of tau by T. Now, denoting theta is equals to T tau by minus Ta, write equation 4 completely as theta by theta I is equals to T tau minus Ta by Ti minus Ta minus exponential of tau minus T. Equating 5 gives the temperature distribution in a solid as a function of time when the internal resistance of the solid for conduction is negligible compared to the convection resistance at its surface. Let's see this diagram where the temperature variation with respect to time in a length system is given. There are different readings on different time are taken. The first is let's say T1, T2 and T3, T4. When the temperature is increased, with the temperature increase, the curve is also increased. Here is a common point, that is 0.368, which are present in all the intervals. Criteria for length system analysis: Biot number and Fourier number. Consider a plane slab. Let the surface on the left be maintained at temperature T1 and the surface on the right is considered temperature T2. As a result of heat being lost to a fluid at temperature Ta, flowing with the temperature heat transfer coefficient Ha, writing an energy balance at the right hand surface. Ka by L bracket T1 minus T2 it's equals to Ha bracket T2 minus Ta. Rewriting the equation, we get T1 minus T2 by T2 minus Ta is equals to L by Ka divided by 1 by Ha, which is equals to R conduction over R convection, which is equals to HL by K, which is known as Biot number. The term HL by K appearing in the RHS of the equation 7 is a dimensionless number known as Biot number. Biot number and temperature distribution in the plane wall is given below as a diagram. Here is the diagram of a wall having thickness L. Temperature changes from T1 to T2 and at last Ta. The heat conduction changes into heat convection. In all the cases when the temperature changes from T1 to T2, the Biot value is counted, where at first T2, when T1 is converted to T2, the Biot number is very less than 1. Then after some time, when T1 is converted to T2, then the Biot number is equals to 1, and in the last Ta, the Biot number is very large than 1. From previous diagram, the temperature profile for Bi is very less than 1. It suggests that one can assume a uniform temperature distribution within the solid if Bi is very less than 1. Situation during transient conduction is shown below. It may be observed that temperature distribution is a strong function of Biot number. Here are some figures of Biot number, where in the first figure it shows that Biot number is very less than 1. In second figure it shows Biot number is equals to 1, and in third figure it shows Biot number is very greater than 1. In all the cases, In all the cases, we had seen that the flow of the lines is changes. That is, in less than is when bi is less than 1, the flow of the lines is almost plane. In the second figure, when bi is equals to 1, the flow is curved a little bit, and in bi is very greater than 1, the flow is all very greater than very we can say it's very much curved. For bi very less than 1, temperature gradient in the solid is small, and temperature can be taken as a function of time only. Not only that, for bi is greater than 1, the temperature drop across the solid is much larger than that across the convection layer at the surface. Let us define Biot number in general as follows. Biot number is equals to HL by K, where H is the heat transfer coefficient between the solid surface and the surrounding. K is the thermal conductivity of the solid, and Lc is a characteristic length defined as the ratio of volume of the body to its surface area, that is Lc is equals to V by A. For solids such as a plain slab, long cylinder and sphere, it is found that transient temperature distribution within the solid it also constant at uniform instant at uniform, with the error being less than about 5% if the following criteria is specified. Then bi is equals to lc HLC by K is less than 0.1. LC for common shapes like plain wall thickness, where thickness is 2L, the LC is A into 2L by 2A, which is equals to L, which is half of the wall. Long cylinder whose radius is R, here LC is equals to pi r square by L by 2 by RL minus R by 2. Sphere, radius R, LC is equals to 4 by 3 pi r cube by 4 pi r square minus R by 3. In cube, side is L, LC is equals to L cube by 6 L square, which is equals to L by 6. Therefore, we can write equation 3 as theta by theta I equals to T tau by minus Ta by Ti minus Ta minus exponential of minus Ha tau by rho CPV if Bi is Bi is less than 0.1. In equation 7.12, which is 12, the equation is important. Its application to a given problem is very simple, and solution of any transient conduction problem must be with explaining if the criteria Bi is less than 0.1 is specified to see in equation 12 could be applied. Now, the term HA tau by rho CPV can be written as follows. HA tau by rho CPV is equals to HLC by K into K tau by rho CP LC square. equals to HLC by K alpha tau by LC square, which is equals to BIFO. Here Bi is HLC by K and FO is alpha tau by LC square, which is FO is Fourier number or relative time. Fourier number, like Biot number, is an important parameter in transient heat transfer problem. It is also known as dimensionless time. Fourier number signifies the degree of penetration of heating or cooling effect through a solid. For small FO, large tau, which is time, will be required to get significant temperature changes. Now, we can write equation 12 as theta by theta I is equals to T tau minus Ta by Ti minus Ta minus exponential minus BIFO if Bi is less than 0.1. Equation 13 is plotted in figure 4, that is this figure given below. Reminder that this graph is for cases where length system analysis is applicable, that is Bi is less than 0.1. In this graph, transient temperature distribution in solid is given where Bi is less than 0.1. Here is exponential of minus x and the graph is versus exponential of minus x by x, and the graph gives a negative slope, a straight line of negative slope. What is the difference between steady state and unsteady state heat transfer? Unsteady state heat transfer is also known as transient heat transfer. Let us see what is the difference between them. Heat transfer is the transfer of thermal energy from a body at a higher temperature to another at a lower temperature. And that means in steady temperature, the temperature difference due to the different temperature difference, there is no change. Due to the time difference, there is no change in the temperature difference. Under steady state condition, the temperature within the system does not changes with the time. Conversely, under unsteady condition, the temperature within the system does not vary with the time. Here, in steady state, as I said, that the difference between the bodies, the difference between the temperature cannot be changes due to the time changes. The heat transfer is constant and the temperature remains constant. Whereas in case of unsteady state, or we can say transient state, the temperature changes with respect to time. As the time increases, the temperature also changes. If the temperature is high, then with respect to the surrounding temperature, then it decreases, and if the temperature is low than the surrounding temperature, then it will automatically increases. Hence, there is only a small difference between them, that is a difference of temperature between the bodies. Thank you. That's all from my side.